yesterday. So we saw that notion of curved space. It's the adequate notion to describe gravity. And the object of interest in a curved space-time is the metric, which actually tells us how to measure distances in a curved background, in a manifold. So we saw that the choice of coordinates shouldn't be important. The physics should be the same. And that is a way to postulate the equivalence principle. So that was initially the first part of the course yesterday. And then we moved into the Einstein equations. Well, we saw the geometric equation and Einstein's equation. So I'm just putting here Einstein equation with a cosmological constant. And we saw that this set of equations, we can derive them from a variational principle using what is called the Hilbert-Einstein action, which is only given by the Rich scalar and a constant, cosmological constant. Moreover, we know that we can go to the Hamiltonian formalism, and in GR, the Hamiltonian formalism is a bit different than from other classical systems. And we saw that the Hamiltonian has to vanish from the equations of motion, and the same as another constraint called the momentum constraint, which actually reduces the number of independent components in our metric to only having 2 degrees of freedom in vacuum. And these 2 degrees of freedom correspond to the graviton. So a massless graviton has only 2 helicities, +2, -2, for those who know about helicity and spin. And in terms of a classical coherent set of gravitons, which can be formed a gravity wave, we can see this idea of 2 degrees of freedom by having 2 different polarizations of gravity waves. And towards the end of the lecture yesterday, we talked about the recent discovery of gravitational waves. So now we'll talk about symmetries and solutions based on these symmetries. So whenever we have a symmetry or an isometry in our solution of Einstein equations, which is generated by a vector field, let's call it K, mu, then this vector field, K mu, is known as a killing vector, and it obeys the following equation. So if you just take the covariant derivative of this one and symmetrize the indices, that has to vanish. So what we call a maximally symmetric space-time, maximally symmetric solution of Einstein equations, is such that it has the largest number of these killing vectors. So in particular, if you are in d dimensions, the number of killing vectors is n times n plus 1 divided by 2. So in Euclidean space, for example, we have that rotations are n times n minus 1 over 2, and translations an extra n. So those are add to the d dimensional number of killing vectors. So as an example, in 2 dimensions, if you just have flat space in 2 dimensions, you have translations in x and y, and then you have rotations. And they all obey this killing equation. So now let's go back to Einstein equations and ask about solutions to those equations that have the maximum number of symmetries, the maximum number of killing vectors. So there are 3 maximally symmetric solutions. Minkowski, which corresponds to having a 0 cosmological constant, and therefore there is no curvature in the system. So sorry, this is in vacuum. I'm not putting any matter in the energy momentum. Another solution is with a positive cosmological constant. Then that curves the space-time. So we have a Ricci scalar that fills that cosmological constant, and the solution is called de Sitter space-time. And if we take a negative cosmological constant, what we get is what is called anti-de Sitter. So we can picture these maximally symmetric space-times, solutions, Einstein equations, using what I call Penrose diagrams. So I will spend a few slides try to explain what a Penrose diagram is. So the first thing is that Penrose diagram can tell you about what is the causal structure of the space-time. That means, for example, if you got 2 points in your Penrose diagram, you know if there could be information traveling from one point to the other one without breaking special relativity. You can also know about topological structure, so we will talk about wormholes and traveling in time. The good thing is that, I mean, these solutions, for example, flat space, they're infinite. However, in this Penrose diagram, I can bring infinite to a finite coordinate. So we can see it in a compact way. We don't need an infinite piece of paper. An important thing is that light, photons, travel always at lines of 45 degrees, or minus 45 degrees. Also, if I change the metric by what is called a conformal factor, which is just a function in front of the metric, they do not change this causal structure, this topological structure of the space-time, and then they can be dropped. So the Penrose diagram of a metric that is conformally related to another metric is exactly the same. And they're very useful to understand, for example, black holes, which will be the next topic. So let's start by constructing the Penrose diagram of flat space. So this is flat space written in spherical coordinates. So I have a radial direction, and then since flat space, it doesn't depend on directions, it's completely isotropic, it doesn't depend on the angles. So time goes from minus infinity to plus infinity, and the radius is just positive. So we can change variables to this u plus and minus, which are just t plus or minus r. And then my two new coordinates go from minus infinity to plus infinity, both. And the metric looks like in the last line, as in the last line. So if I start with that metric, I can now bring infinity to a finite distance. And for that, I can use a trigonometric function. So the arc of the tangent function. And then I bring infinity to pi over 2. And the metric looks now in the form below. Then I can go back to something like time and radius, as I had before, by choosing now a combination of u plus and u minus. And this will be something like my new time and my new space. Eta my new time, chi my new space. And then I get this metric, which has a conformal factor, so some function of eta and chi in front that I don't care about. And the rest looks very similar to the flat space time I started with, but instead of the radius in front of a sphere, unitary sphere, I get the sign of my radial coordinate, new radial coordinate. So how does that look like? Well, since these things are, so once I reach pi, we're talking about angles, so pi and minus pi are identified. What I get is that on the chi direction, this thing is connected. And so what I get is this slice of the cylinder, that's what I'm mapping. This is, so I'm forgetting about the angles. So each point on this slice or on this surface of the cylinder has half of a 2 sphere. Now I can just take half of that surface, and then I can attach a full 2 sphere on each point. And this is what is called the Penrose diagram of flat space. So let's see what are the different ingredients. So the lines of constant time are these ones. The lines of constant radius, these are the vertical curved lines. And we have several other points or places. So the first one is this future time like infinity. So remember, observers, massive observers, move along time like geodesics. Well, that's where they will end up. So all humans will end up at infinite time, will end up at that point. Then we have the future non-infinity. So this is so remember, light always travels at 45 degrees. So if I am here where this light cone is, and I emit light, it will travel at 45 degrees, and at infinity, it will touch what is called scribe plus. That's the name of that letter. I plus is simply special infinity. And we have the same, so scribe minus and I minus, which are just equivalent to I plus and scribe plus, but taking time to run backwards. So they are just the past. So that is the way to visualize flat space in this compact way. And now we will move into the other two maximally symmetric space types. So the first one is the jitter. So as I told you, it's a space that actually has curvature. So the Riemann tensor is non-vanishing. The Ricci scalar is just proportional to the cosmological constant that is positive. And the easiest way to picture this space type is by going to 5 dimensions. Just like, for example, when you have a sphere, you cannot picture it in 2 dimensions. The easiest way is to go to 3 dimensions and then put the sphere. Here, the easiest way to picture the jitter, 4-dimensional the jitter, is to go to 5 space. So I just add an extra coordinate, so flat space in 5 dimensions. And then the jitter corresponds to having a constraint, which is actually a hyperbola. So, of course, I cannot draw the 5 dimensions. So I'm just drawing 3 of those 5. And then I'm putting a hyperboloid, generic hyperbola. So I got 5 coordinates, but then I have a relation between those 5 coordinates. That means I only have 4 independent coordinates. I can choose different representations or different frames of these coordinates. And if I do that, I can write the jitter in different useful ways. So the first one is what is called the static coordinate patch of the jitter, which is the following. So this looks like flat space plus a correction in dt and dr. And this correction only depends on the radius. It doesn't depend on time. So this is why it's a static metric. It doesn't evolve in time. I can also change my coordinates and go to what is a cosmological reference frame of the jitter. And then what I get is the following line element. I don't know if you recognize this from your cosmology course, but this is a Friedman-Robertson-Walker spacetime, which has a scale factor that grows exponentially. And actually, it grows with the power of the cosmological constant. So this exponential expansion is actually extremely important for the concepts of dark energy and early phase of the universe called inflation. So what is the Penrose diagram of the jitter? Well, remember this was flat space. The jitter actually has an extra set of pieces where you have that future infinity, both the time-like one and the null one, so I plus and scribe plus, they all converge into this one, both of them. So it's not a point anymore, it's a line, horizontal line. And the same for the past infinity. And special infinity, now it's this part. So the first thing you see is the word horizon. So let's see what that means. So we got 2 special kinds of horizons that I want to describe. One of them is called the particle horizon. And for that, you can imagine that some event happened in several points of spacetime. Let's say there was an earthquake, for example, here. And then there is an observer that is evolving in time. Let's say, imagine that it's not moving, it's just, and then a few I don't know, nanoseconds later, calls people. So that is the other event here, the black hole. Well, actually, on this spatial slice, there are points that can affect the call of my observer, but there are also other points that cannot affect the call. Why? Because they are not causally connected. That means if someone here sends information, which can only travel at the speed of light, it goes at 45 degrees, it will never reach my observer making the call. So that means we separate this slice into a region that is causally connected to that event and a region that is not causally connected to that. That means this line represents the horizon. We split the space-time into two. The other horizon, which is the one we saw for the zeta, is the following. It's called the event horizon. So imagine this is infinity, special infinity, and imagine I am an observer. And at each point on my trajectory, I'm sending light away. So I'm using a flashlight or a torch, and I'm just sending photons away. So they travel at 45 degrees. So the observer is just emitting light, and this light is escaping towards special infinity or null infinity. However, when I cross this horizon, then light, since it has to travel at 45 degrees, it reaches this other surface, which is null infinity. It's not null infinity. That means space-time is also split into two. We have a region where light cannot escape and reach infinity. And that will be relevant for black holes as well. So, in that sense, here if I have an observer that moves here, after this it cannot emit light that will reach special infinity. And where do we see that horizon? In this static patch of the zeta, in this static coordinate system? Well, when r is equal to square root of 3 over lambda, then this term here goes to 0, or this one blows up to infinity. That is why we cannot actually see beyond certain, now that we have a dark energy phase, we cannot see beyond certain distance from the Earth. That's what is called the Hubble horizon. So now let's go back to these maximally symmetric spacetimes, and we have the zeta, the last one, until the zeta, sorry. And that one is exactly the same as the zeta, but the cosmological constant is negative. And to picture this spacetime, the easiest way is also to go to 5 dimensions, but now instead of adding a normal special coordinate, I have to add another time. So another minus sign in the metric. So I have 2 times. And now the zeta is just this other hyperboloid. So it looks like this. Now the problem with this is that actually I have the time, it goes along the vertical axis, and I have curves that can go back in time. So I can actually go back and kill my grandfather. Which would be definitely a problem. Of anti zeta. However, one can manage to go to unfold this spacetime and go to something that doesn't have that problem, and that is what is called the universal covering space of anti zeta. So how does it look like? Well, in these static coordinates, it looks very similar to the zeta. The only thing is that you got a plus sign instead of a minus sign, and that's why in this case you don't have a horizon. So the Penrose diagram, you can try to write it, but it's not very helpful. You don't actually get something that looks compact, just points and separated from space, so it's not very useful. However, this space-time will be very useful for the people who will stay in the string theory part of the lectures. Because of that, what is called the ADS CFT correspondence. So far we have described solutions with 0 cosmological constant in vacuum, that are maximally symmetric. We have flat space. If we have a positive cosmological constant, we have the zeta. If we have a negative cosmological constant, we have anti-zeta. So now I want to discuss what happens if we got actually a point like mass. So the space-time is not maximally symmetric anymore. Why? Because there is a special point in there, which is where the mass sits. And that's what gives rise to what is called the Schwarzschild solution. For that, there is a very nice theorem. So actually, the symmetry that we're looking at is a spherical symmetry. So I can just write down what is the most general spherically symmetric metric in 4 dimensions, and it's the following. So these are unknown functions of t and r. So you cannot depend on the angles, because depending on the angles will break spherical symmetry. And I have 4 functions. However, remember, I always have a choice of coordinates. So we saw before that we could choose 4 coordinates. However, because I have a spherical symmetry, only time and radius are my free coordinates. So I cannot mess with the angle. So out of these 4 arbitrary functions, I can actually, there are only 2 that are relevant. 2 are physical. So I can choose this off-diagonal element, one that has dt dr, f1, to be 0, and I can choose f3 to be r squared, so that corresponds to a sphere of radius r, the last piece. So when you put them in that answers this idea of metric into Einstein equations, you find the following. First, there is only one solution. Remember, Einstein equations are differential equations of second order in your metric components. So in F0 and F2, you got differential equations of second order. So what you find is that the solution is unique. It's only one solution. Also, you find that it doesn't depend on time. So you don't have to assume that it is static at the beginning. You find that from the equations of motion, from Einstein equations. And then the last thing is that, yeah.
Where the term, the second one comes from? Because all the line elements.
This one?
Yeah.
So if you just decide to write down the most general metric that has spherical symmetry, it actually has to have these 4 functions. That's the only possibility. So in principle, so this term doesn't depend on the angle, so that actually preserves the spherical symmetry. However, since you got this choice of coordinates, you can always choose it to vanish. And that's why in most of the textbook, they start by not putting it. But that's because they have already taken the choice of a reference. So the last property when solving Einstein equation is that, remember, we have differential equations of second order for F0 and F2. So in principle, we should have 4 integration constants. And actually, we only get 1. So how does it look? Well, that's what is called the Schwarzschild solution. And it looks like the following one. So you go to 1 minus 2 times Newton's constant times the mass of the central body divided by r, and then you get the same factor in the r piece, but sitting at the bottom. So since the solution is unique, it can describe from black holes to planets, to whatever thing that is spherically symmetric. So why? Well, because if you got a black hole or a planet of a given radius, you know that that's outside your vacuum. And the vacuum solution of Einstein equations is unique. It's the Schwarzschild solution. Therefore, the Schwarzschild solution is extremely important because it can describe most of the things we see in nature, if we assume they are spherically symmetric. So let's see how this Schwarzschild solution looks like. So we can put a test particle on this Schwarzschild solution, and then just by playing with the questions, you can get to something that looks like energy conservation. So you can have a kinetic term for this test particle, where r is the coordinate of the test particle moving towards the Schwarzschild or away from the Schwarzschild solution. We can have a potential. Well, we have a potential, sorry. And we have that this test particle has a given energy. So for this particular solution, which is the Schwarzschild solution, the potential has the following form. So the first term is just a constant, forget about it, doesn't really matter. The second term is the Newtonian potential. Third one is your angular momentum. So you have seen this is just the usual two-body problem that you get in mechanics or under a gravitational field. And the only thing that is different from that, from Newtonian mechanics, is the last term, which is the only GR correction that you get. And that GR correction is actually what makes Mercury not to follow elliptical orbit as the other planets. I mean, well, in principle, none of them follow elliptic orbits, but to a good approximation, they do. However, Mercury is the one that actually goes away by eye from that approximation. So we can rewrite that potential in the following way, where we get a factor of r minus 2g and m. What happens is that for radius smaller than 2gm, the potential goes negative, and what it means is that the particle cannot actually escape the Schwarzschild solution. So it cannot go away from it unless it's traveling faster than the speed of light. So what happens is that, for example, for stars, the radius of the star is always outside this 2g and m. However, black holes, and that's actually the definition of a black hole, all the matter of the black hole has to be inside this radius, what is called the Schwarzschild radius. So, we'll see a picture of how it looks like, well, kind of, and it will be more clear what I mean by you need a velocity that is faster than the speed of light. So let's continue discussing the metric of Schwarzschild. So we can see that it has two problems at a given radius. So when r is equal to 0, this term blows up, and this term goes to 0, and this term goes to 0. So pretty much the whole metric, you've got one piece, time, that goes to infinity, and the rest goes to 0. We have another problem, which is when r is equal to the Schwarzschild radius, that means 2gm, and then we have that this term goes to 0 and this term goes up. So let's see what are these two singularities. So the first one is called a true singularity. Why? Because if I calculate the Riemann tensor, the Ricci tensor, or the Ricci scalar, they all diverge at that point. And the problem is that, remember, so scalar functions are tensors of 0 rank, they don't have indices. And when I go to a different reference frame, they are exactly the same. So if I calculate the Ricci scalar and that one diverges, that means that it doesn't matter to which coordinate system I go, it will always diverge. However, when I take the Schwarzschild radius, that's actually what is called a coordinate singularity. It's just, I'm just taking a bad coordinate system. My variables are not the right ones. So for example, I can go to this u and v, which are called the Kruskal variables, and there, the metric is the following. So it's a very strange combination of r and t, these variables. The metric is not particularly beautiful, but nothing wrong happens at the Schwarzschild radius. Okay, so we got two different singularities. One is real, the space-time breaks there, general relativity doesn't work there anymore, and the other one is just a bad coordinate system, the same as r equals 0 in polar coordinates. So, even though it's the Schwarzschild radius is not a singularity, there's still something funny happening there, and we'll see what happens. So if I got two observers, one very close to the black hole, falling into it, and another one pretty much at infinity, and the first one is emitting light as it travels towards the black hole, and the second one is receiving them, the guy at infinity sees the guy close to the to the black hole, moving slower and slower and slower as it approaches the Schwarzschild radius. Not only that, it actually takes an infinite amount of time to reach the Schwarzschild radius. However, one actually crosses the Schwarzschild radius at a finite time, and when it crosses the horizon, R and T change signs in the metric, so the radius now becomes something like a time, and the time becomes something like the radius, and it goes exactly all the way to the singularity. So from an observer far away, we can never see people falling into black holes or matter falling into black holes. It will take an infinite amount of time to see it. However, the people or the matter falling into the black hole, they do it in an infinite time. So if I can just do a not very accurate diagram of how this sheet, remember space-time, we can think of a sheet, and then Einstein equations tell us how it gets deformed by the presence of matter. A black hole will be something like this, where we have a big throat, then we have the matter at the very center of the black hole, and there is this event horizon. And imagine if you cross this event horizon, and if you try to send light out, it's really hard to climb up all this potential. And then light cannot escape to infinity. And that's what I mean that actually once you cross this, not even light can escape. And that's why we call it a black hole. So what is the Penrose diagram of a black hole? Well, it actually has, it's like flat space. Remember, this is my patch of flat space. I can draw just a square or a triangle. Both of them are the same. And there's a horizon. This is the Schwarzschild horizon. So, and if I'm emitting light, I can reach null infinity, so an observer at infinity. But once I cross the Schwarzschild radius, then this light gets trapped and reaches the singularity. And we tend to draw singularities on Penrose diagrams with these wiggly lines. But just as a mathematical curiosity, I can just extend this space-time and just analytically continue it. And what I get is that actually I can get a singularity in the past. That's what is called a white hole. So information comes out, and that's opposite to the black hole, where information just goes in and nothing comes out. And I can have another space attached to it. So if I live in space A, there will be a parallel space-time B, so it will be a parallel universe. And there is a wormhole here. The problem is that you cannot cross it because it's only on special direction. So we'll have to, move at an infinite speed to cross it. So we can construct more general black holes. And the first thing you can think of is what happens if I add rotation. So if I add rotation, I construct what is called the Kerr black hole. There is a similar Birkhoff theorem that tells me that the solution, again, has the mass. Remember this Schwarzschild radius, I have the mass. And there is another parameter, which is just the angular velocity of your black hole, this J. And the metric is quite awful. And then it's got a funny physics. So apart from this event horizon, that means where this factor goes to 0, I get what is called the ergosphere. And that is the following. If I have this black hole that is rotating this way, this direction, and I have a particle that is actually rotating in the opposite direction, as it falls into the black hole, once it gets into this ergosphere, it actually has to start rotating in the same way as the black hole. So this is a place where even if you got an initial angular velocity in the opposite direction, you have to change it. Another way to say it is that if you've got a particle here, which is moving with the black hole inside the ergosphere, and I'm outside the black hole, and I want to see this particle static, I will have to move faster than the speed of light outside to see that particle static. with respect to me. So we will see the parent growth diagram in a second. If you add now charge to the black hole, you get what is called the Weiser-Nordström solution. So the charge is this Q, and this one has a nice metric. Oh, actually, just one thing, sorry, before I forget. So there is a bound for the angular momentum of the curved black hole. It has to be always smaller or equal to a given power of the mass, right? And what is called the extremal case is when it is equal to the mass. And these are very stable solutions. They're called BPS. And for the stringies, you will see them more when you see D-branes and instantons, solitons, and things like that in string theory. However, also in nature, it seems that a lot of the astrophysical black holes that we see in nature are very close to being extremal. Okay, so if you add charge, you get what is called the Weiser-Nordström, and there is also a condition about the charge with respect to the mass, and the extremal case is when you take this associated radius with the charge, with the Schwarzschild radius when that is 2 times. And now you can think of adding charge to the black hole and rotation, and you construct what is called the Kerr-Neumann solution. So all these three black holes, they have a similar parent growth diagram, and it's the following. So we have our flat spacetime, and then we have this horizon that we cross. However, we don't reach the singularity of the black hole, but we reach another horizon. There's always a second horizon. And you can see it in the Kerr metric easily. So this is a second order equation in R if you want it to vanish. So you have two solutions. So one is this first horizon, the other one is this second horizon. And then the singularity is not horizontal, it's not space-like, but it's time-like. It's there. So now what you can do is to continue analytically this spacetime, and you get these several copies of the spacetime that go forever. And then I think you have more interesting situations. So if this is our spacetime, this universe, remember we have this parallel universe we cannot get into, but then we can actually cross the two horizons. We don't have to actually reach the singularity. So we don't have to get into the R equals 0 of the black hole. And we can actually appear into this white black hole and get into a new universe. So this is another kind of wormholes where you can actually have observers that can go from one universe to another. In reality, when you put real observers with matter, you tend to destroy these bridges. You need to be a bit more careful on how to build some that are more stable. So there's a conjecture about black hole, or a theorem that says that black holes do not have Kerr. And what it means is that imagine that you got matter that collapses into a black hole, and actually on that matter we have, the Don Quixote book falling into it. So Don Quixote's book has a lot of information in it, right? However, when it collapses into a black hole, all that information goes into mass, charge, and angular momentum. Nothing else. But then, I can tell you that black holes are not that black. They emit radiation, so this is a quantum process. We're not going to talk about it. It's called Hawking radiation. And black holes emit radiation isotropically. It means the same radiation everywhere, in any direction. And this radiation is proportional to the mass of the black hole. Therefore, a black hole that doesn't get more mass, doesn't accrete more mass, at some point it will evaporate because it's emitting radiation all the time. And it will evaporate in a time that is proportional to mq. But then we got a problem, right? Because the Don Quixote's book, with all its information, fell into the black hole, right? And the big question is that then the black hole evaporates. It disappears. So where did the information go? Question. Hawking bets on it every 2 years. Every other bet he wins it, and the rest he loses. So what is interesting is that the radiation has a temperature, it has an energy, it's photons, and the energy is directly related to the surface gravity of the black hole. What is the surface gravity? Is the gravity that you will feel exactly at the horizon. So it's like here in the Earth, the surface gravity is that little g, the acceleration that an object feels. Okay, it's given by little g. Well, the surface gravity of the black hole is exactly at the horizon, and there's a relation between the temperature and the properties of the horizon. So that starts connecting this idea of black holes with thermodynamics. So we will talk about that in the next slide. So we have here the 4 laws of thermodynamics. So the 0 law means that you get constant temperature when you're in thermal equilibrium. That translates to a black hole as the following statement. You have a constant acceleration at the horizon for a black hole. The first law of thermodynamics that relates internal energy, heat, and work, at the black hole level relates the mass, the area of the horizon. Remember, the horizon is just the surface. It doesn't depend on the angles, it's just at the Schwarzschild radius, so it's really a compact surface. And since it's a compact surface, it actually has a finite area. So it relates the area, the angular momentum of the black hole, the charge, to the mass. And it has exactly the same form. Now, the most important law, the second law of thermodynamics, that says that the entropy only increases in time. It's, for the black hole, it's the same as the area of this horizon only increases with time. And the third law, it says that you cannot reach zero entropy on a finite, or zero temperature on a finite series of steps. And that is equivalent to a black hole as not reaching zero acceleration. So there's a key connection between temperature and the surface gravity and entropy and the area of the horizon. And the way to relate that is that the entropy of a black hole is just a quarter of the area of its horizon. So now, think in terms of thermodynamics. When you have a thermodynamical system here, you know that the entropy scales as the volume of the gas, for example, that you have inside. For black holes, it actually scales as an area. That is very strange. So it looks like we actually need less information than the volume. And that's what gives rise to all these ideas of holography, always called the ADS-CFT correspondence. So there are key implications of that, and there's still, it's an active field of research within gravitation, within string theory, and some other condensed matter systems. So that's what I have to say about GR. Now, for the rest of the course, I would like to tell you about going beyond GR. So I'll talk about this construction of general relativity based on paper by Desser. Something about a theorem, how unique GR is. It's called the Lovelock's theorem. I'll talk about some problems with GR and why we have to go beyond that. And we can modify GR in 2 different ways. One is at high energies, what I call the UV, ultraviolet, high energies. And then in the infrared, it's actually low energies. So let's start. Is GR really unique? Is it really special? So this is work that was pioneered by Feynman, Weinberg, Hallward, and Kreischer. But really, there's a finite statement that is quite nice. So for electromagnetism, we got that the vector field, the gauge field, which can spin one particle, doesn't couple to itself. That means we don't have photons interacting with photons. Light doesn't interact with light. And that's why we can have fiber optics, right? Because if we send light, 2 different signals, they will never interact. And that's why we can get optical fibers. However, in gravity, the graviton, which is the one that carries the gravitational field, it actually interacts with itself. And that means it contributes to its own energy momentum tensor. So it's in the same way as Yang-Mills does. So what Tesseract did was to construct Einstein's theory from having just a theory with free gravitons. So free gravitons coupled to an energy momentum tensor that is made out of gravitons again. And the idea, the assumption is that the stress energy tensor is symmetric. That's an assumption. Another assumption is that we only have second order derivatives in the construction. We don't care about total derivatives in the action. They are boundary terms. And a key assumption is that we get local Lorentz invariant. So if you try to write general relativity in terms of the metric, what you get is an infinite series. So you get infinite number of interactions. But if you use the right variables, it actually simplifies to just one interaction. And we will see what is the idea. So the idea is to take linear gravity, where we're expanding the metric around flat space. Remember, we had this H. Where I'm taking the connection as an independent field. So remember, this was the Palatini formalism. So then you know that gravity has to generate its own momentum tensor. There is a way to construct that, which goes by the way of one of the authors, very funded. On the other hand, if I take full GR, and I write the equations of motion of GR, that means Einstein equations in terms of H and this gamma, I find that the two things are exactly the same. So that means if I start with simple gravitons and an interaction between them, I recover GR. That's the only way to actually do it. So let's see how it works. So if I start with just free gravitons, written in terms of H and gamma, this is the action that I get. So this is the Lagrangian, sorry. And it goes by the name of Fierce and Powell. Was developed at the beginning of the 20th century. And remember, H is just a perturbation around flat space. That means the full metric I removed flat space, and what I'm left is with H. I'm just putting here on a scale. And gamma is the connection, the one that defines the covariant derivatives, and I'm assuming these are two independent variables. So what do I want to recover? So this is my free theorem. This is just gravitons at the linearized level. And I want to recover the Hilbert-Einstein Lagrangian. So remember, the Hilbert-Einstein Lagrangian is the following: is square root of the determinant of G times the Rich scalar. So if I expand this equation in G and gamma, what I get is the following. The first term is just a total derivative. You can forget it. This piece is exactly what I have here, is the first Pauli action. And then I get a cubic interaction between the gammas and the H. So general relativity is just a cubic interaction in this language. So I only need to explain a cubic interaction. So if I have done this only with a metric, only with H, I would have to construct here an infinite series with respect to H. So how do we couple the first theory, this first Pauli theory, to an energy momentum tensor? Well, we do it in the following way. So we just have this H coupled to the energy momentum tensor, and that means that the equations of motion, what I get is that box, the wave operator acting on H, is the energy momentum tensor. That is exactly the same equation that we saw for the gravitational waves. So that is just linearized gravity. So this Belifante approach to construct an energy momentum tensor is, imagine there is a fictitious metric. I call it gamma. Right? I can always covariantize my metric. That means whenever I see a metric, a flat space metric, eta, I put a gamma. And whenever I have a partial derivative, as I have at the top, I put a covariant derivative with respect to this new metric that I put gamma. Now, that defines a new action. So now I know that I can construct an energy momentum tensor, which is actually the energy momentum tensor that I need, just by taking the derivative with respect to this fictitious metric called gamma. And what I found is this expression here at the bottom. It's just a partial of h times gamma times plus gamma squared. So let's just see if that is exactly the same as what I would get from this cubic interaction. So this Hilbert-Einstein term, remember, is just the same first Pauli action plus a cubic interaction. So what are the equations of motion? The equations of motion are the following. These two, that's a Palatini formalism, and then if I combine them, I get that the linearized equation, it's actually the box operator I get on the left, and on the right, from this cubic interaction, I get this term. And this term is precisely the term that I calculated using this Belli-Fanti approach. So what I have proven is that I can do linear GR coupled to its own energy momentum tensor, and it's the same as full GR. So that is a bottom-up approach that is taking a theory of gravitons and building up GR. So something else we can do is to ask, in a general framework, is GR unique? So if we demand second-order differential equations, if we only care about gravity being propagated by a metric, it's a spin-2 field, massless field, and we're dealing with 4 dimensions, then the only consistent equations of motion are Einstein equations up to a constant. Now I do an experiment, I throw something here and there, and I know I have to fix the constant so that I recover Newtonian law. So that means Lovelock's theorem states that GR is quite unique. So what are the implications? Well, one of the implications, for example, is that this combination of R squares, which is called the Gauss-Bonnet combination with Riemann's Ricci tensors and Ricci scalars, cannot be within the theorem. And we know that it has second-order differential equations. However, they're only dynamically in 5 dimensions or above. In 4 dimensions, they're topological. That means they're just a total derivative at the level of the action. So another implication is that if you want to modify Einstein equations, then you have to break some of the hypotheses of this theorem. So you have to either consider more fields. So apart from the metric, this spin 2, I have to put something else. You have to, another possibility is to accept higher order derivatives. However, that usually tends to lead to instabilities, problems, mathematical problems. You can give up the number of dimensions. You can say, okay, now I go to 5 or more dimensions. You can change the symmetry in the indices of the equations. You can give up the divergence of the field equations. That means you can give up the conservation of energy. And another thing you can do is to, since we give up writing up differential equations, I'm perhaps thinking of things like integral equations, where you have things that are non-model. So that is what I need to modify GR. Now, the big question is, why do we want to modify GR? So what are the problems of GR? So one thing is that it's non-renormalizable, and we will talk about this, what I mean by this. There are essential singularities, so we've seen the R equals 0 point in the black hole. That is where GR breaks down. It doesn't work at that point, so we know there is a problem. We also have the Big Bang singularity at the time equals 0 in a Friedmann-Robinson-Walker background. And we also know that every time we do cosmology, it seems that we need to put something strange and special at the early universe. So that's because the usual model based on GR, it doesn't solve a few of the problems that we see in cosmology. So what about at low energies? Well, it seems that at low energies, we have a dark sector in cosmology. That means we have what is called dark matter. And is it really a particle, or could it be just a modification of gravity? I mean, the way we measure things might be wrong, and that's why we need to modify gravity. And we also have another component which is a bit more exotic, which is this dark energy, this accelerated expansion of the universe, and it has some problems. From the theoretical point of view, it has a very small observed value. We don't understand why today it's happening. And we have a problem with the vacuum energy. So the energy, sorry, the vacuum is not that empty. It actually has energy. And that energy gravitates in the same way as a cosmological constant. However, its value is massive. And and we'll talk about that. So this might all be connected to problems, properties of the theory at high energies. So what else do we have? Well, recently there have been some problems with the model based on GR of the universe. So it's called lambda CDM. And here, for example, we have different data sets, and you can see that they all not match at the same time. So that's creating tensions. You can also see that lambda CDM, which is this GR model, which is the blue line, doesn't really align very well with the dots, experimental dots. They like to stay under the line for some given observables. And finally, more recently, we have seen that this scale factor, which here I'm parameterizing as this Hubble parameter, seems to like having oscillations, these wiggles. Whereas lambda CDM, which is GR, it just has a straight line. So then if we want to go away from GR, we open Pandora's box, and we have thousands of possibilities, infinite possibilities, right? And as I told you, you have to modify Lovelock's theorem, so you can go to higher dimensions, you can get strings, you can get branes, you can give locality away, so you can have, for example, operators which are 1 over a derivative. That is strange. We can talk about that if somebody doesn't understand what is to operate with something that is 1 over a derivative. We can take higher order derivatives, so we can have, for example, an arbitrary function of the Ricci tensor in the action. That's called FR. We can add new fields, and then we have a soup here of things. And we can also add, for example, tensors, vectors, scalars. So since there are too many options, I'll talk about some that I find interesting or that I just have important things to say about. So let's go first to ideas of how to modify GR at low energies. So the problem I want to focus on is the cosmological constant. This is a dark energy phenomenon. So a simple solution is just having a cosmological constant. However, there's a problem with the vacuum energy. So we can have a more complicated solution based on new degrees of freedom, in particular new gravitational degrees of freedom. That means I'm modifying general relativity. So what do I need? I need a new theory that maybe has some beautiful principle behind it, and then it's tied up with observations. It explains the universe. And in this link, I might find new physics. Okay? So let's see what is the problem of the cosmological constant. So if you calculate the vacuum energy, so remember we know from quantum field theory that the energy has virtual particles there, so it's not that empty, the vacuum. Sorry. And since we believe there is Lorentz invariance even at that level, then its energy momentum tensor of that vacuum energy should be something that behaves as a cosmological constant. So it's just a constant times g mu. So that means the vacuum gravitates as a cosmological constant. So that means there is an effective cosmological constant, which is the sum of the one I put by hand in my theory and the vacuum energy. However, from experiments, that means the expansion of the universe, I know that it has to be tiny, its value. It has to be very close to 0. That means this one I put by hand has to pretty much cancel the vacuum energy. And there is a really fine-tuned cancellation that we don't like in physics. And we don't like it because it doesn't come as something natural. So why is this vacuum energy so big? Well, we can estimate it perturbatively. So let's just imagine that in the vacuum there are harmonic oscillators. So the only thing we know how to do in physics is harmonic oscillators. Let's assume, and that's just free particles. So let's assume the free particles. So I'm summing free particles from zero energy to a given energy that is where my theory is valid. I'm just putting the energy of a harmonic oscillator. So I sum them all, and what I get is the following expression when I do the integration. The first few terms you can actually do quantum field theory tricks. So that means randomization and get rid of them. But then this third term that actually behaves like the logarithm of your cutoff, your higher energy that you're taking, stays there. And this term actually scales as the mass of the particle that I'm putting in, this harmonic oscillator. So now I can think of, well, there's only not one kind of species, but several kind of species. So that means if they are fermions, they contribute to a -1. If they're bosons, they contribute with a +1. and then I can add them all. So if, for example, I only had electrons in the world, right, I would get a vacuum energy that is scaled pretty much like the mass of the electron to the 4th. And that is 10 to the 33 milli-electron volts. And that is a lot, well, to the 4th. And that is something like 30 times larger than the observed value we have for the dark energy. So the problem is that, and this gets worse. I mean, if you take the Planck scale, for example, then your problem goes to 120 orders of magnitude. So imagine, I mean, if for having a factor of 2 wrong in your exams, they put you the question wrong, the answer wrong. Well, here we have a problem in physics that has 120 orders of magnitude wrong. So this, by a lot of people, is considered the worst mistake in a calculation ever. Okay? So, what are the possible way outs? Well, we can have cancellations, very specific cancellations among contributions. So I told you that, for example, if you got fermions and bosons, they contribute with different signs. So supersymmetry that you would see in this course actually has that contribution of canceling things. However, we know that there is no supersymmetry at this energy scale. Here, there is no supersymmetry. Therefore, we still have a problem. So we can cancel a few orders of magnitude of the problem, which we still. There's a no-go theorem. That means a theorem that forbids something. And if you imagine that the universe is expanding, maybe the vacuum energy is just relaxing. Right? You started with a very big vacuum energy, but then the universe expands and relaxes this vacuum energy. And it gets smaller and smaller. Well, there's a theorem by Weinberg that tells that that's not possible. So another idea is to go to modified gravity. So let's start by describing where can we modify gravity. So this is where we have measured gravity. So remember, if I take Einstein equations, I forget about the evolution in time. I only think in terms of spatial gradients. Then my differential equations, Einstein equations, are second-order differential equations. That means I need 2 integration constants to get a unique solution. So we can plot 2 things, for example, the curvature, and something which is related to the Newtonian potential, so this 1/r scale. And then I can put plots where we have measured gravity. So here we have the solar system, we have the Earth, we have satellites, we have pulsars. Up here at the right corner, we have neutron stars, black holes. Below that, we have supermassive black holes, which are at the center of the galaxies. This red line on the right represents, you cannot go beyond that to the right, because that means you actually have to violate special relativity. You have to have that the speed of light is not the largest speed you can have. And then here at the bottom, you have cosmology. So you have got galaxies, clusters, the peaks of the CMB, microwave background radiation. And then where have we put constraints? So we have put constraints here at the level of the solar system, and then you can go to the left, and here in the Earth we have labs that have put constraints on the gravitational force. So they do Cavendish experiments, famous experiments in Washington, state of Washington. It's called the A of Wash. And they have put bounds on how far we can modify GR, because we haven't seen any modification. We have advanced LIGOs in these black holes. There will be LISA and this also a timing array looking at the far right. And then we have cosmology here at the bottom. So what is true is that at the solar system, we have very tight constraints on gravity. So by, for example, sending lasers to the moon and getting them back, getting them reflected on mirrors, we can actually see the precision of, or we can measure with a very accuracy, a lot of accuracy, the position of the moon with respect to the Earth. And then we can see if there is a modification of gravity with respect to it. And the precision we get with these experiments go to, let's say, errors of 10 to the minus 14, or 12. So that means we can have a deviation of the order of 1 divided by 10 to the 12. So that means if I, here at the Earth or around the solar system, I don't have a deviation from general relativity, but then continuously I try to get a deviation at the cosmological level, then I might also get a deviation on black holes and neutron stars. So that means I need a mechanism when I modify gravity such that at the cosmological level I get a modification in gravity, but then once I get to the solar system energy scales, I actually get GR back effectively. And there are 3 known screening mechanisms. So remember, I'm modifying gravity. A simple way to modify gravity is by adding a new degree of freedom. So not only the metric, but I have something else. And that something else, the simplest thing is to consider a scalar field. So if I consider a scalar field, and I put a generic equation of motion for a scalar field, a simple one, might have a kinetic term, a mass term, which is just the potential, and how it couples to normal matter, how it interacts with normal matter. Now, if I only care about non-relativistic matter, which is what we see in space, so things that are not traveling fast, then I don't couple on it to the energy, full energy momentum tensor, but only to the density. So pressure is negligible. So the first screening mechanism is what is called the chameleon mechanism. And here the idea is that I change the mass of my field depending on the environment. So if I am in a very dense environment like the Earth, the mass of the chameleon goes up. That means I cannot excite that mode. That means I don't see it, and then it doesn't contribute to gravity. I only get the piece that comes from the graviton. However, if I am in a very low density environment, the mass is very small. And then it's really easy to excite this mode, and it can actually explain dark energy. The second option is the strength of how it interacts with normal matter. I can also change it according to the environment, and that's what is called the symmetron mechanism. Finally, what I can also do is to modify the kinetic term, and that's what is called the Weinstein mechanism, or a good realization of that is what is called the Galilean field. So, what is the most general action I can, or Lagrangian I can write in 4 dimensions that has an extra scalar field apart from the metric? Well, that's given by Hornbeskis. He wrote it in the 70s. Now he's a famous painter. He sells his drawings very well. He was at Princeton. Nobody cared about his work at that time. Now he has a lot of citations, which has become popular. And it actually is the most general theory with an scalar and a tensor, the metric, that has second order differential equations. And it's actually horrible. So here at L4, you actually have the rich scalar. So if this arbitrary function, G4 of the scalar field and X, its kinetic energy, the kinetic energy of the scalar field, is 1, then I recover general relativity. Otherwise, I go away from general relativity. So you can see that it has several unknown functions of the scalar field, and this is the most general thing you can write. So it doesn't have beauty there, but one would expect that there would be, a subset of those, of all these terms that might be relevant for physics. In particular, for example, to solve the cosmological constant problem, this vacuum energy problem, there's a subsector called the FAB4, and it was developed by Moses et al. In 2011. And the idea is that it's a sector that, for example, Minkowski is always a solution in vacuum, even if you have a cosmological constant. We know that is not true in GR. We've seen that the maximally symmetric spaces are de Sitter, anti-de Sitter, and flat space. Flat space was only a solution if the cosmological constant was 0. So in GR, oops,
there is a connection there.
Yeah, maybe we have that.
And is it Schwarzschild a solution?
Good question. No.
Oh.
Well, no. Yes or no? Oops.
So that like
No. So there is no Birkhoff theorem. There is no Birkhoff theorem. That means Schwarzschild is not the only solution.
Okay, but it is.
For some terms, yes. For not for all of them. So the thing is that so this Rondesky, but it still has a lot of freedom. You can also play with several. And so anyway, what I want to say is that Minkowski is a solution, even if you have a cosmological constant. But not only that, this solution remains a solution, even if I get a phase transition that changes the cosmological constant. So if I get a cosmological constant that suddenly grows, flat space-time is still a solution. Goes by 4. All these terms that I have here, only 4 of them remain, and they go by the name of Paul, Ringo, John, and George, and that's why it's called the FAB4. So that's just one example of things one can do with modifications of gravity at the level of the infrared to deal with dark energy. So with some studies here, we're actually working on, for example, using this Rondesky Lagrangian to get dark matter. And if any of you is interested, I suggest you talk to Francisco, who is there at the back. We can talk to you about it. So what do we have in the UV? So in the UV, where is the problem? So we talk about this non-renormalizability of general relativity. So let's see in simple words what it means. So consider having a scalar field. So this is the action of a scalar field that has a kinetic term and an interaction, self-interaction with an n power. So it's phi to the n power. So let's just do a rescaling. So I send t to bt. So for example, if b is very small, I'm talking about very small times, that means very high energies. If I take it to very large b, that means going to very large times, that means lower energies. So by demanding Lorentz invariant, I have to change times and space in the same word. So that means x has to rescale also with 1 power of b. So then you can do power counting. So you can put here the b's in the kinetic term. So you got dt, d3x. So you got 4 powers of b. And then you got derivatives. So that's 1 over b. So you get 2 negative powers of b. So that means in total you get b squared. So that means that if my field rescales as b to the -1, then I don't get any powers of B on the kinetic term. Well, if I do now, taking that my field rescales as B to the -1, now I plug it into that potential, what I get is that the potential rescales as B times to the 4 minus n. So if n is equal to 4, what I get is that it's invariant. This is a very important theory, and it's related to n equals 4 supergiant mills that you will see in your stringing courses. However, for example, if you take n to be larger than 4, then you get negative powers of B. And if you go to very high energies, that means small b's, then this term blows up. So that is the normalizability. So at high energies, these terms blow up. So right now we're dealing with a scalar field, but we'll see the connection it has with here. So another way to see this same problem is to see what are the units of this constant that I put in front of the potential term. So if I take units of mass of this thing, I get that it actually has 4 minus n. And they're coming by the power counting of each of these things. So again, if n is bigger than 4, what I get is my coupling constant, my constant in front of the potential. It has negative mass units. Just so that, I mean, you've seen the quantum field theory course, and you saw that whenever you have a kinetic term like this, your propagator goes like 1 over k squared, and I don't have a mass term. So I'm not putting a phi squared. So now let's go to general relativity. So if I take the linearized Lagrangian of general relativity, it's precisely that first Pauli Lagrangian that I showed you, or the one I used to derive the gravity wave equations. It has the following form. So I just have H, remember this is a perturbation around flat space, and then I have some differential operator of second order times H. So again, the propagator schematically goes like 1 over k squared. And if you check the coupling, the dimensions of the coupling constant, Gn, in front of the theory, it actually has negative dimensions. So it actually has the same problem as that scalar theory that I mentioned before. And that's why GR is non-renormalized. So within quantum field theory, there is a way to cure these infinities at high energies. That is renormalization theory. So we can actually put an infinite number of extra terms to eat these divergences. The problem is that it has to be infinite number. And not only that, due to Lorentz invariance, they have to be powers of the curvature tensors. So it has to be, you know, Ricci square, Ricci cube, Ricci fourth scalar, but also the Ricci tensors and the Riemann squares, cubes, and blah, blah. So this is an infinite series in all of them, with different coefficients. So if I linearize this new action with all these new terms, I get something that my differential operator gets modified to something like a differential operator squared. So that means that the propagator, it not only looks like 1 over k squared, but it actually has contributions from this Ricci squared, Ricci to the fourth, and blah, blah, blah. So the propagator just, you can see it just like so. Inverting this kinetic term, it goes like k squared minus a term that actually has k to the fourth. Now you can just do a split of fractions, and you can get a term that goes like the usual massless GR propagator, 1 over k squared, and another propagator that has a mass, like it's proportional to the Newton's constant. However, it has the wrong sign. It has a minus. So if the GR propagator has a plus, this one has a minus. That means it comes from a negative kinetic term. So imagine you build up a Hamiltonian. It will be a term in the Hamiltonian that has negative kinetic energy. You've never seen that. Why? Because imagine a normal system where the Hamiltonian has a negative kinetic energy. That means I can increase the energy of the one that has a positive term, decrease the kinetic energy, increase also the kinetic energy of the one that has a minus sign, and get the same energy. So without wasting energy, I can speed up things. It's even better than the perpetual machine. So that's what is called a ghost, and these are very pathological things. And that's what it usually happens when you have higher derivatives. So all these terms here, they give you equations of motion that have more than 2 derivatives. So 3 or 4 time derivatives. So possible way outs. So again, we can do supergravity and get cancellations. That is supergravity. Well, adding supersymmetry, that gives you supergravity. And you get cancellations, but it doesn't work. The other thing you can do is to give up Lorentz invariance. And then make that space and time act differently. That, for example, one proposal is this Hojava-Lipschitz theory. Another thing you can do is to study things non-perturbatively. One idea is asymptotic safety by Weinberg. Another idea is to go through this quantization of gravity using path integrals. And we have, for example, here the wave function of the universe with this Wheeler-DeWitt equation. Or we have something called spin forms that I don't know anything about, so you might want to ask experts here in Mexico. We can also change a bit the canonical quantization prescription, and we can also get the Wheeler-DeWitt equation that we talked before, or something what is called the loop quantum gravity. Or we can actually forget about GR and put new physics there. So not only changing the quantum prescriptions, but changing GR, and we can put new physics. So one idea is, for example, to think that GR is just an emergent phenomenon. So there is a new theory by Berlin now that's becoming popular. And another idea is that, for example, we actually have algebraic structures. So what is really fundamental is an algebra. It's just a group and an algebra. And space-time is only something that comes out of that. It's not fundamental. There are these BCJ amplitudes that I also don't know anything about, but they come to adding new physics. And for this audience, I guess string theory will be another way out from these non-renormalizable properties of gravity. And with that, I'll finish. We have plenty of time for questions. So, anyone? No questions? Yeah?
Which ways gravity helps
So it's pretty much the same idea as the cosmological constant problem. Fermionic loops count with the opposite sign as bosonic loops. So if you have the graviton and a gravitino, will contribute in the loop corrections with the opposite sign. So that will help to bring the divergence down, but they don't get removed. They get milder. Anyone else?
More questions for Gustavo?
Yeah.
When you talked about the problem, you said that there was a time divider in the calculus and the calculation.
So you mean here? Yeah. Nothing is here.
Yeah. So what's the way today in the transference problem?
Oh, yeah, for me it's not such a problem, but a lot of people put it as a problem. And it's so the universe is accelerating its expansion now. And by now, I mean recently in the history of the universe. And the big question is why?
So
I mean, why it didn't start expanding like, you know, in 10 billion years later, or actually at the beginning of the universe? So why now that we can observe it?
There is evidence about the subject. Isn't it?
Yeah. So yeah, for me, I think it's just the fact that it's small will give you that. So I don't think it's a huge problem, but historically people have said it's a problem. Anyone else? About cosmology?
What the proposes in his new theory of emergent gravity?
So it goes back to this idea. So what he's proposing is that since entropy scales as an area, he's saying that maybe dark energy is just a new underlying set of microstates where the entropy of those states, they're quantum states, they are entangled, and the entropy scales as the area, and it gives you dark energy phase. And now what happens is that when you calculate this medium, the interaction of that medium with normal matter, you get an effect that looks like dark matter. So it actually helps you to explain dark energy and dark matter. The big problem is that he doesn't have a theory. So these are just like ideas. I'm not really. There's no really a theory. Anybody else? You can ask in Spanish as well.
These white holes are possible?
White holes? Mathematically, yes. Whether they exist or not, that's the question. I think it all has to do with solving the black hole singularity. That will really tell you if they exist or not. I mean, if they can really form in nature. So mathematically, they should be there in Einstein theory of gravity. But since you need to solve the initial singularity, that might prevent them from existing. Otherwise, you can actually get information out from nowhere. Just like a black hole eats information, these white holes expel information. So you can get Don Quixote. Just not exactly. Anybody else?
I didn't understand totally the information.
Okay. So the first thing is that, yeah, black holes are only characterized by the mass, the angular momentum, and the charge, nothing else. Whereas if you take anything else in our universe, it's characterized by a lot of things. Right? I mean, color, flavor, Don Quixote by lots of words. So it has information. The first problem is like, okay, imagine you got matter falling into a black. So that matter has information. When it goes into the black hole, it gets translated into only mass, angular momentum, and charge. So there we're kind of losing information. However, we know that, I mean, if we only believe in GR, the classical theory of GR, then that information gets trapped within this horizon. Right? It cannot come out. So then you don't care if you lost information. It doesn't come out, the problem doesn't come out into our universe. However, due to quantum processes, we know that black holes are not that black. They emit radiation. So that is a calculation you have to do based on quantum field theory of this Schwarzschild black hole, for example, Schwarzschild background. And what you realize is that the black hole actually emits radiation. And this radiation is isotropic. I mean, it's not that the black hole emits radiation only in that direction, because that is information. It's like saying, okay, emitting in that direction, but not in that one is giving you information. Right? giving you that direction. That's information. It actually emits all directions the same way, so that is isotropic. So that it doesn't have a lot of information coming out this radiation, apart from its energy. So then, the big question is, okay, if nothing else falls into the black hole, and this black hole keeps emitting radiation, it loses energy, loses mass. So it starts shrinking, 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 shrinking. And it gets to a point where it just evaporates, disappears. And then the big question is, if nothing special happens at that evaporation, then what happened to the information? Because now you really put, for example, the color of your t-shirt when you're falling into the black hole, and it came out as just isotropic radiation. So where is that information? Because now it has come out into your universe. It's outside in our universe here. So where is it? So, yeah, there are, yeah, as I said, I mean, Hawking always proposes a new idea. And I think, I would say most of the new ideas are based on this path integral approach to general relativity. And it has to do with topology of your path integral in a complex plane. It's a bit complicated, but it has to do with really what happens at evaporation. And yeah, some people say that, yeah, I mean, there will be like a big explosion of information as well, and then you get the information path, or really, you know, the information just disappears. The universe just stays happy. But yeah, it has lost a lot of it. So it used to be very popular like 10, 15 years ago. Now it has died off. Nobody cares that much.
Can black holes lose information on Mercury?
So, two things. So, no. So, in that sense, you do change. So when you have a merger of black holes, you change the property of the black hole at the end. Right? And then the rest of the energy just release it mostly in gravity waves. So you do get the information kind of back. What is true is that you don't know what happens to the quantum behavior of the black holes. So all the simulations we have with merging black holes, they're classical. So they don't deal with the quantum processes. So I don't know if something will happen there, but I think that's a tougher question. I think it's easier just to study one first simple black hole that is not moving, not doing anything, and see what happens to the information there, and then ask about two that collide. But yeah, initially I would say it's a very hard question, like the full one with the quantum. You agree?
Well, actually, because at the beginning you have two black holes. Each of the black holes you have the mass, the spin, the charge, and at the end you have one.
Yeah,
so
but
that loses information.
yeah, but in terms of gravity waves, so it's in the gravity waves. So I'm saying is that, I mean, okay, in other words, we can reconstruct the black holes just by having the shape of the gravity wave. That's information. We can get back the angular momentum, the mass, and the spin. So that means we got the information. So, yeah. You got it.
But actually you can always do that. You have matter that is black hole, also have the information.
But once it is inside a black hole, you cannot say, oh, what it felt, it was a blue t-shirt, another black hole.
Also the same two black holes. One is
Oh, but once once the matter is inside the black hole, it has lost its information. Then the collision, it doesn't help.
You said that a black hole uses its mass, and well, in that case, it uses surface area in the web.
Yes.
And then the entropy of the black hole goes down.
Yes. But that is okay. I mean, you know that in a closed system, you can have a part of the system that loses entropy, right? It's just the whole system, isolated system, cannot increase its entropy, right? But of course, this radiation is taking the extra. So in that sense, there is no problem. Yeah.
Why the graviton interact with itself?
Why does it interact? So there is no explanation as why, for example, the gluons interact with themselves. It's just nature. What is true is that it does, and that's a big difference with respect to electromagnetism. So just photons, they do not interact with themselves. So it just happens. I mean, that's nature. You could have thought that in a parallel universe, for example, the laws of gravity are completely different, and then gravitons do not interact with themselves. There is nothing fundamental that tells you that you are forced to have gravitons interacting. If they do, then it seems that you need to get GR. If you don't, then you get linearized gravity, which is just a reduction of GR and killing all the interaction. Yeah, it's just nature.
But in the case of the gluons, it's due to the non-abelian nature of the group.
That's our explanation, right? It's the
Yeah.
same here. But it's really nature. I mean, another example is that you got another force in nature, which is electromagnetism. You've got also some bosons there that are the photons, and they do not interact. And for that, you need a an abelian.
Yeah, that's right.
So these gluons, I mean, a priori, it's not that. So we don't have a fundamental way of saying like, oh, because my fundamental theory is this, then gluons have to behave like that. In principle, it's the opposite. It's, okay, we observe gluons and we try to model them, and we have to use a non-abelian. So, I mean, the hope is that, for example, string theory will provide you these answers. But I don't think it can provide the answer at the level of, so, let's see, level of the graviton. So you're assuming something. In string theory, you assume that strings interact. And then you're putting the interaction mechanism. So you again assume that gravity is interact. So yeah, I don't think you can explain. But maybe their gluons can be explained. Well, that's a hope. Of course, nobody has known. More questions?
Graviton could be detected with gravitational waves.
So that's what you are detecting. It's just a coherent state of gravity. So just a single graviton? No, but for that you actually need a quantum experiment. The problem is that then the energies are extremely high, so you will never reach those energies in the lab. So we have to go maybe to the early universe. So we know that the Big Bang singularity is our best laboratory, or the singularity in a black hole. And there we could claim that we detected gravitons. But it's always through indirect detection. Very, very low.
Can you please explain again how to go from one universe to another universe without one hole? Is it something about velocity, which needs to be higher than the light?
So there are several wormhole constructions. So the one I showed you here was just a continuation of space-time. So, for example, imagine you have in space-time that it has a variable, let's say p, and p has to go from 0 to infinity. Then you say, okay, what happens if I make p negative? Well, nothing. Still solution of Einstein equation. Oh, Okay, so I just take this new spacetime that actually has p positive and p negative, and they represent two spacetimes attached. So what I show you is that for the Schwarzschild solution, there's a wormhole there, but it's connected through. I mean, if you want to go from one to the other one, you have to move on a space-like trajectory. And the problem with space-like trajectories is that you have to go faster than speed. So you have to cross from A to B. So that means you have to actually have a line that is below this 45-degree line. That means traveling faster than speed. Well, that's for this one. For these other ones, well, we have seen that there is a universe here and there is a universe up here. And in these ones, you can just follow a trajectory of a normal observer and you can end up in a new universe. And there are all the construction supplies. Of wormholes.
Why is that why do you need to put more than one?
Oh, so this is exactly what I'm saying. Like, for example, you got a variable that you can continue it analytically, and then you can patch another spacetime, but it's really another spacetime. So the Penrose diagram of these black holes is this one, and that's where it stops. More questions?
In one by one, you put anti-ozone. What is anti-ozone?
Anti-horizon. Oh, no, that's just, so maybe it was a word that people use. So I got this one. So, for example, here they call it past horizon. Maybe another one they call it anti-horizon. So these horizons are like horizons, but from the, so this is like a white hole now. So coming out, so let's go to the Schwarzschild. So you've got a white hole, now you're coming out here. So information only comes out, but cannot get in. So that's why this one they call it anti-horizon. Really, from my description, it's only a horizon. But that's just the name of it. Yeah.
Now it seems to me that getting more data and getting more acquiring information about the early waves in LISA, for example, is not useful because all the problems you solve are or seems to be very quite apart of the theory of the development for getting new requirements. So, do you think that is the way to get this the better way to get a requirement in LIGO or LISA, for example?
No, the opposite. The information is extremely useful to probe GR, to test GR.
Yeah, but
so actually you're getting new information. As I tell you yesterday, by looking at gravitational waves, it's a different channel to all the observations we had before of the unit. Most of them were based on photons, electromagnetic spectrum. A few of them were based on neutrinos. And we cannot do really cosmology with neutrinos. With these things, it's really a new arena. It's a new thing. And the good thing is that it complements the other ones. So actually, this pattern here that you see, which is the merger of this black hole, it's very, very susceptible to the mass of the graviton, the interactions of gravity, and everything. So just by looking at these patterns, we can put strong bounds on the theory of gravity. So actually, we're getting a lot of information. Now, we're all very happy with this. This will be a big future in our community. Yeah. The opposite. I mean, maybe I didn't stress it. No, we're extremely happy. They should get the Nobel Prize this year. More questions? If not, we can go, I guess, to the coffee, and there you can ask me questions. Yeah.
But actually, I think that locker is some good companies.
Hopefully, it's faster.
So basically around
So it's here?
upstairs.
Upstairs. Okay. So maybe.
You will have more.
So then
Well, I
just
think that-
wait a few minutes and then we go all upstairs.